I'm going to continue where we left off. So in the last session, we saw how to write basic Solidity code. We saw these basic contracts. We saw how to write the King of the Ether Throne contract. And even before the last session, we talked about the concept of a puzzle contract. This was the idea that I have a contract like this. I've already written it here. So I have a function called deposit where anyone can basically use this function to pay the contract. It's a public function, so anyone can call it. Anyone can create a transaction calling this function. And it's also payable, so they can also attach some money when they're calling this function, and it will be paid to this contract, right? And I also have another function called claim, which basically takes some value x and then computes the hash of this value, and it uses the SHA-256. And it says that if this hash is some particular value that I have hard-coded before, then just pay all the money in this contract to whoever called this function, okay? So it's a puzzle. Anyone who can solve this puzzle would be able to claim the entire contract's balance. Okay, now, we've talked about this before, and this is actually vulnerable to a front-running attack. Now, on Remix, I just have a virtual machine, so I cannot show you a front-running attack. You have to just pretend like this is being executed on the actual blockchain, and you have to think about what happens here. So suppose that I have put this contract, I have deployed it on the blockchain. I mean, I can do at least the deployment. Let's say I deploy it. And now, suppose that I also deposit some money. So let's say I deposit 5 Ether into this contract. Okay, now the balance of the contract is 5 Ether. And now let's say that someone else comes and they know what value of X to use in order to be able to claim this price. Now, honestly, I don't know that because I cannot invert a hash function. So I don't know what value of X will have this hash. Actually, I'm not even sure if this is a valid hash. But anyway, suppose that someone knows a value of X that is an actual solution to this. What do? They want to call this function claim. So they create a transaction that basically calls claim, but also includes the value for X. Now, they will propagate this transaction using the gossip protocol. So everyone else on the network will see this transaction. But the transaction also contains the value of X. Now, let's say you're a miner. You want to add a new block. Would you add this transaction to your block? Well, if you're rational, if you just want to maximize your own payoff, it actually makes sense to steal the value of X. It makes sense to create another transaction in your own name, where you are basically the MSG.sender, which uses the same value of X and calls the same function. So what's happening here is that there are 2 transactions. There's the first transaction, which was the honest transaction, but it was not yet put on the blockchain. The miner could see this transaction, and based on that, he could create another, let's say, dishonest transaction. But as long as this dishonest transaction appears before the honest transaction on the blockchain, the miner gets paid. Right? So this is called a front-running attack, and it's basically like front-running in a queue. You look at the transactions that are already available, but they're not mined, and based on those, you create another transaction, and then you hope that your transaction gets on the blockchain before the previous transactions, right? And of course, if you're a miner, you get to decide what to put in your block, but even if you're not a miner, you can do this kind of attack. So let's say I'm just a normal node on the network. I see a transaction that is calling this function claim and has the right value of X. Instead of propagating it, I just create my own transaction which uses the same value of X, and I try to propagate that. If I get lucky and my transaction gets on the blockchain first, I'm the one who's going to get paid. So generally, this kind of thing is considered a vulnerability. So you should never write contracts that have these kinds of problems, especially in your homeworks and in the final project of this course. So how can I solve this vulnerability? How should I write my contract differently? Any ideas? Well, I can do something like commit and reveal that we've seen, especially in homework 1. So I know that if I just say what my value of X is, someone else might steal it. So instead of doing that, I can first commit to my value of X. And then only after I have committed to it and everyone knows that this value belongs to me, I actually reveal it. Okay. So let's say I'm Alice. This is what I want to do. I know the value of X, but I'm afraid of revealing X because someone might do a front-running attack. So I'm just going to choose some nonce n, and I'm going to take the hash of X and n. Okay. And I'm going to announce this to the contract. And I'm also going to announce n. So let's say the contract can save these things. So I have a function called commit, and this is also a public function. Now, what I want to give this function is actually the hash. So let's call this h. So bytes 32h. By the way, I don't really talk about the types in this course because this is not a Solidity course. Learn Solidity on your own. And sometimes my contracts don't even compile because I'm sometimes writing pseudocode because the type conversions are just hard in Solidity and you have to figure it out all the time. Anyway, in my commit function, I'm going to give my hash and I'm also going to give this nonce n. So n, okay? Now, the contract is just going to save it. So how can a contract save something? Well, I can just have a global variable, or actually what we call the storage variable. So let's say I have a variable here called committed h. And let's say I also have a variable called committed n. And let's say I also want to keep the address of the person who made the commitment. And I'm going to call that Alice. Okay. So whenever I call the commit function, I would just say that committed h becomes h, and committed n becomes n, and Alice becomes msg.center. Now, of course, I don't want to allow many different commitments. So I want to allow only one commitment. Of course, you can also have an array of commitments if you want to, but I'm just simplifying here. So let's say I want to allow only one person to commit. So I will also have a Boolean called committed, which is of course originally false. And whenever I commit, I say that committed is now true. And at the very beginning, I require that no one has yet committed. Okay. So this is my commit function. And by the way, I don't want this to be free because someone might just commit as an attack because this now stops other people from committing. So I also say that if you're doing commit, you have to pay some money. Okay, so I'm going to make this payable, and I'm going to also require that this function call contains some amount of money. So the amount of money in the function call is in msg.value. So I just ask that msg.value is some particular amount, whatever. You can just hard code something. You have to pay this much in order to commit. Okay. Now, so I had a solution, X. I didn't want to reveal X. So I just computed the hash of X and N. And I basically gave the hash H, and I also gave the N and also my address. And this is how I commit. But then when I want to claim, I can say I reveal the value of X. But here I'm going to check that X is a solution to the puzzle, whatever my puzzle was. My puzzle was also a hash puzzle. It can also be any other puzzle, as long as you're just checking some property of X. But I say additionally, I want this X to satisfy this. I want to make sure that this is the X that was committed to before. So hash of X and N should be H. So if I take the SHA-256 of X and N, this is going to get a compiler error because I have to merge them better. That has to be H. Okay. Now, of course, I also had like committed N, and this also has to be committed H. Okay. The compiler error is because of type conversions. Like you can't just use commas, you have to use a function to actually concatenate the data. Anyway, but just consider this as a pseudocode. Now, this one makes sure that no one can steal my solution, right? Because if I'm Alice, I would first choose a random nonce n, and I would first commit to my solution. So I calculate the hash h, which is just the hash of the solution x and this random nonce n. And then I announce h and n. And the contract just saves that. Of course, I have to also give a deposit, right? And then later on, whenever I call claim, this should match. But one other important point, here, instead of saying that I just pay whoever called claim, I can say I just pay Alice, right? So now with these changes, if when I'm calling the function claim, someone tries to do front running, fine, they're just paying my gas fee for me. At the end of the day, I'm the one who's getting paid. Alice is always the one who's getting paid, right? Now, does this completely solve our problem? Well, not really, because now the question is, what if someone does front running on commit? Right? So I cannot do front running on claim because by the time Alice wants to call claim, the commitments have already been done. Oh, by the way, I have to also require that there has been a commit before here. So if Alice is calling the function claim in her transaction and Bob wants to do a front running attack, sure, Bob can create his own transaction using the same values, but at the end of the day, it will just pay Alice, right? So front running on claim doesn't work. But what if I do front running on commit? Suppose that Alice wants to commit, she's calling the commit function in her transaction, and then at some point, let's say Bob is the miner, Bob sees this commitment and he says, I'm just going to steal the commitment for myself. Well, that's possible. He can do a front running attack, but two problems. The first problem is that in order to do commit, you have to actually pay a deposit. So now Bob has to pay the deposit if he tries to steal Alice's values of h and n. And secondly, if Bob is successful and he's actually the one who gets committed, then Alice would simply not call claim and would not show the value of x. So Bob will lose his money. So there's no incentive for Bob to do this kind of attack. Okay. Now, of course, you can also have some time locks. Basically, you can say when you commit, your commitment is valid for a particular number of blocks. So remember, you can access the block number. So you can say when I do a commitment, I save what was the block number in which the commitment took place. And I say that this commitment is valid for, let's say, only 100 blocks. So when you commit, you have to claim within 100 blocks, otherwise your commitment is invalid. Okay. If I make that kind of change, then anyone who does front running on commit would just lose some money, and then their commitment will also expire after, let's say, 100 blocks. And then the actual person who knows X can make another commitment. Okay. So this is a front running attack. Generally, in this course, we're going to cover a lot of attacks, and I'm going to also release a final project soon. The way this works is you should first try to do the final project, and then after every lecture, you will hear about some attacks, and you have to go and look back at your code and make sure none of those attacks are applicable. Okay, so let me now show you another contract and a different kind of attack. So imagine I want to write a contract for a joint bank account. Okay, so I'm going to create a new contract called joint accounts. Let me just copy this part. Joint accounts. Okay, so this is just a contract that, let's say, allows Alice and Bob to create a joint bank account. So I'm just going to hard code the addresses of Alice and Bob. And the idea is that anyone can pay money into this account, but only Alice and Bob can withdraw from it. Okay. So I'm going to have an address Alice, and let's say I use this first contract here as Alice. I'm just hard coding the address. And let's say I also have Bob, and suppose Bob is the second contract. Okay. So I have Alice and Bob. Now, I'm going to write a function deposit that anyone can call, and this function can just deposit money into this contract. By the way, I want Alice and Bob to also be payable so that I can pay them later. So I say these are address payable, and then I have to also make these payable. Okay, and this one is also payable. Okay, so I have a function called deposit. This is public and payable, and it doesn't do anything. So it's just a function that accepts payments. Anyone can call it, anyone can include any value of payment, and then that payment will belong to the contract. Okay, and then I'm going to also have a function called withdraw. This is also public, so anyone can call it, and any contract can also call it. But I'm going to check that the caller is either Alice or Bob. So I'm going to say require msg.sender to be Alice or Bob. By the way, when you're writing require, you can also add an error message so that if it fails, it gives this error message in the log. So it just says you're not Alice or Bob. Now, if the message sender is either Alice or Bob, I'm just going to pay the money to them, right? So I say the recipient is going to be payable msg.sender, and then I just say recipient.transfer, and I just want to pay, let's say, all the value in this account, or I can also ask them to tell me how much they want. So let's say they give me some number X and I pay them X. Okay, so very simple contract. It doesn't seem to be vulnerable because it seems like it just works like a normal joint account, right? Anyone can deposit, only Alice and Bob can withdraw. But we're going to see a ton of different vulnerabilities here. So first of all, let's just deploy this contract and let's pay it some money. So let's say I'm deploying it. So joint account is deployed now. And let's say I deposit 5 Ether. Okay. Now I have this joint account and it has 5 Ethers in it. Now, again, this is something that I cannot do in the virtual machine, but I just want you to imagine what happens if this kind of situation comes up in the real world. So let's say both Alice and Bob want to withdraw at the same time. Okay. So they both create transactions and each of them wants to basically take out the 5 Ether. So I have transaction 1, which is created by Alice, and it calls withdraw for 5 Ether. Okay. By the way, these values should be in vase, so 5 Ether would be 5 times 10 to the power of 18, if I'm not mistaken. And let's say there is a transaction 2. This one is created by Bob, and it also calls withdraw 5 Ether. Okay. Now, what's going to happen here? Well, first of all, we said that we cannot create new units of currency. The only way that new units of currency are created is by mining. When the miners add a new block, they get some block reward. That's how new units of currency are created. So a contract cannot create new money. So this means that if the miner, suppose, puts transaction 1 first and then puts transaction 2 in the block, transaction 1 will be executed first, and that would withdraw 5 Ether from this contract. So Alice will receive all of the 5 Ether. But now the contract doesn't have any money at all, right? The balance of the contract is 0. So now that the balance of the contract is 0, transaction 2 is being executed. So it passes these tests, and here the contract tries to transfer 5 Ether to Bob, but the contract doesn't have 5 Ether. So this causes an error. It's basically, it throws an exception. And this means that the entire function call and the entire transaction containing that function call, the transaction of Bob, is going to be reverted. I'm sorry, can you keep it down? Yeah. Okay. So basically, whenever you have any kind of error, your transaction gets reverted. And when it gets reverted, it means that you lose your gas money, but any other side effect of that transaction, whatever else that transaction did, is undone. Okay. So in this case, if transaction 1 is put in first, Alice pays for gas and gets her 5 Ether. And then transaction 2 is executed, Bob pays for gas, but he doesn't get any money because the transaction gets reverted. But on the other hand, if Bob's transaction is put on the blockchain first, then Bob is the one who gets the money and Alice's transaction will get reverted. So there is now a competition between Alice and Bob. They each want to have their transaction on the blockchain first, right? Now, this is bad because basically the result depends on the order of transactions, and the order of transactions is decided by the miners. So here we've written a contract in which the miners have a lot of control. The miners are the ones who can actually decide who gets the money, Alice or Bob. And that's terrible. You should never write contracts like this. But it gets even worse because any of the two parties can actually bribe the miners to put their transaction first. Okay, so most miners would just put the transactions with more transaction fee first. That's just the heuristic that a lot of them use. So in a case like this, Alice can just create this withdraw function. And remember that you can set the gas price. You can say how much you're willing to pay the miner for every unit of gas. And Alice can just choose an outrageously high gas price. So Alice can say something like, I choose a gas price such that 1 Ether is paid to the miner. Okay. If she does this, then it's very likely that the miner would put her transaction first. But this is no guarantee. And anyway, it seems like the miner will get the money even if he puts Alice's transaction second. So this is a bribery attack that is not guaranteed to work. Can we do a better way of bribing miners? And it turns out, yes. So again, suppose that you're Alice and you want to make sure that the miner is incentivized to put your transaction first. Okay. Instead of paying a high transaction fee, instead of setting your gas fee outrageously high, you can do this. You can first basically empty your account. So if Alice has a lot of money, let's say she creates another account, transfers almost all of her money to the new account. Okay, so at this point, I want to say Alice's account contains very little money. And it's very little money because I want to make sure that it can only pay for gas. Okay, and then there are these transactions. And let's say after these transactions, Alice creates another transaction. This is transaction 3. And this transaction doesn't really do anything. Let's say it just transfers money again to Alice, but it pays a lot of transaction fee. Okay, so this is created by Alice, pays, again, let's say 1 Ether in transaction fees. Okay. Now, Alice is going to publish both transaction 1 and this new attack transaction, whereas Bob has just published transaction 2. Now, let's look at it from the point of view of a miner. If I'm a miner, if I put Bob's transaction first, Bob gets paid. But remember, Alice's account is almost empty. So now I'm running Alice's transaction. She doesn't get the money. She just pays for the gas. But now I cannot put in this transaction because Alice doesn't have 1 Ether to pay 1 Ether in transaction fees, right? So if I put Alice's transaction after Bob's transaction, then I cannot put this last transaction and I cannot get paid 1 Ether in transaction fees. On the other hand, if I put Alice's transaction first, then Alice gets paid 5 Ether. Bob's transaction gets reverted because there's not enough money here. And then now Alice's balance is 5 Ether plus whatever money she has left from the gas money and so on. So now she can afford to do this transaction 3, which means that as the miner, if I put transaction 1, 2, 3 in this order in my block, I actually get paid 1 Ether. But if I do 2, 1, 3, I don't get paid 1 Ether. And actually my block would be invalid because at the point when transaction 3 wants to get run, Alice doesn't even have the transaction fees to pay for it. Okay. So this is another way of bribing the miners. And again, very important that you make sure this kind of thing does not happen. Okay. But another important point is that, well, we are just hard coding Alice and Bob's addresses here. So because I'm hard coding them, I'm sure that they are external accounts. I just hard coded the addresses of an external account. But in general, when you have an address, you cannot assume that it's an address of an external account. Okay. So it might be that this is the address of a contract. And if it's a contract, things would be very different. So let's say I have a function here, for example, called register that can be used by anyone to sign up in this contract. Okay, so let's say that I don't have any values for Alice and Bob. I just have 0 for Alice and Bob initially. It has to be converted to address. And it's payable for now. And let's say anyone can register to become either Alice or Bob. So whoever calls register, if I don't have an Alice, I make them Alice. Otherwise, if I don't have a Bob, I make them Bob. So I say if Alice is 0, Alice becomes msg.sender. Otherwise, if Bob is 0, then Bob becomes msg.sender. Okay. Now, of course, this is kind of a stupid contract to write, but I just want to show you how this would work out. So let's say I have a contract like this. Anyone can call register to become Alice. Anyone can call register to become Bob if there's already an Alice. So the first 2 people to call register would become Alice and Bob, basically. Okay. And now anyone can deposit. Only Alice and Bob can withdraw. Now, the important point here is that I have no way of checking here if the address for Alice is actually an externally owned account or if it's another contract. So here's what Alice can do. Alice can create another contract. Let's call it Alice's contract. And then this contract can actually call the register function in this contract. So I want Alice's contract to become the Alice in joint account. Now, how can I do this? Well, basically, I need to know the address of joint account on the blockchain. So let's say I have a function here. I don't know what to call it. Let's call it register in joint account. And it's going to get some address. And this is the address of a contract. And I'm just going to create this thing, joint account. Let's call it my account. And I do something like this. So I say, look at the contract at the address JA. And this contract is a joint account contract. And then I'm going to say, just call the register function. So I say my account.register. Okay. Now, and let's say this is also public. Let's see what happens. So let's say I first deploy joint accounts. Now, as soon as I deploy a contract, that contract will have an address, right? This is the address of the joint account contract that I just deployed, right? So now I deploy, let's say, Alice's contract. And as you see, I have Alice's contract here, and Alice's contract also has an address. So now I want to call this function register in JA of Alice's contract, but I want to give it the address of the joint account contract. So I just copy the address of the joint account contract, I put it here, and I call the register function. So what's happening here is that I'm calling this function in Alice's contract. I'm giving the address of the joint account. So this contract is now calling the register function of this contract. Okay. So now, if I ask who's Alice, oh, I just realized that I've forgotten to make it public. Sorry, I have to do this again. So let's say this is public, and this is also public, so that I can easily see the values. So again, I'm deploying joint accounts. I'm deploying Alice's contract. I'm taking the address of joint accounts and giving it as a parameter to this function, to this register in JA. And now if I ask who's Alice, you see that this actually contains the address of this other contract. Okay, so a contract could register in my contract list. So here, all I'm saying is that I have this contract called joint account. And well, on the blockchain, the way things work is that I can have many different copies of this contract, right? I can have many instances of this. Maybe I've deployed it many times. And each instance is going to have a different address. So every time that I deploy it, I can also see its address, right? So now here, when I want to talk about joint account, I cannot just talk about one contract joint account. I have to say which joint account at which address. So I take the address, and this is how I would create basically a pointer to the joint account at that address that I can use to call the functions. So all this is saying is that find the joint account at this address, call it my account, and then call my account.register. So my account is an instance of joint account. Okay. So here in this joint account, now I have this other contract as a basically as Alice. It has registered. Now, why is this problematic? It's problematic because now I can use my second contract, basically this Alice's contract, to also bribe the miners, right? So what can I do? Let's say I want to withdraw. So remember that I can check my own balance, right? So I can have a function like this. I'm calling it bribe miner. And again, it's going to take the address of the joint account. And let's say it's public. I mean, in practice, I will have some requirement here that only I myself can call this function, but it doesn't really matter at this point. Let's say I copy the same thing. Now, instead of doing register, I'm going to call withdraw. Okay, so I'm saying my account dot withdraw. And let's say I want to withdraw some amounts, 5,000 Wei. Okay, now, after I do this, I'm going to pay some money to the miner. How can I pay money to the miner? Well, I need to know the address of the miner. But we've seen before in the global variables in Solidity that I can actually get the address of the miner. That was basically Solidity global variables. It was called, I think, Coinbase, right? Yeah. So if you look at block.coinbase, that's the address of the current miner. So I can say block.coinbase.transfer some amounts. Again, you get to choose your amounts. So basically, the only thing that this bribe miner function is doing is that it's first withdrawing money from the original contract, and then it's paying some money, some part of that money to the miner. Now, in practice, these numbers have to be much larger because, again, these numbers are in Wei, so you need 10 to the power of 18 to get 1 Ether. But I don't really care about the numbers here. Now, what's going to happen? Why is this a successful bribery? Because again, imagine that Bob is trying to withdraw and Alice is also trying to withdraw, but instead of directly calling withdraw, she's calling bribe miner in her own contract. Okay. Now, again, look at it from the point of view of the miner. If the miner puts Bob's transaction first, Bob is going to withdraw, let's say, all the money in the joint account. And then this call to bribe miner comes second, right? So this one is going to call withdraw, but this withdraw is not going to succeed because the joint account contract doesn't have enough money, right? So here, when it wants to transfer 5,000, it doesn't have 5,000 to transfer. So it throws an exception. But these exceptions basically propagate. So because withdraw throws an exception, then bribe miner also throws an exception, which means that bribe miner is also reverted, which means that the miner doesn't get any money, right? But on the other hand, if the miner puts bribe miner first, then this withdrawal succeeds, which means that this contract now has the money and it can also pay the miner. So the miner also gets this money. And then afterward, he can put the transaction of Bob. That transaction will not succeed. It will only pay for transaction fees. And so this is another way of bribing miners. Now, one thing that is really important about these exceptions and reverting transactions or function calls and so on is that when a function call is reverted, all of its side effects are reverted. So I can have this in the other order. So let's say in bribe miner, I'm first paying the bribe to the miner and then I'm doing withdrawal. Okay. It doesn't matter because this basically does the same thing as before. Because suppose that the withdrawal fails. Suppose that the joint account does not have enough money for this withdrawal. Then the withdrawal is going to basically cause an exception at this line. And that exception is propagated to bribe miner, which means that the call to bribe miner also gets reverted. But when it gets reverted, the money that was sent to the miner, that is also a side effect. So that's also getting reverted. So even if we get reverted here, whatever happened here is going to be reverted and the miner is not going to get its money. So again, this is another way of bribing miners. Okay. So let's say I do something else. Suppose that instead of saying that my joint account, when we want to withdraw, it pays all of the money to Alice or all of the money to Bob, I can also say that it pays half of it to Alice and half of it to Bob, right? This makes sure that it would always be fair. So let's say I have this joint account. Again, anyone can deposit into the joint account. And anyone can also call withdraw, or only Alice and Bob can call withdraw. But no matter who calls withdraw, half of the money is paid to Alice, half of the money is paid to Bob. Okay, so let me just write this. So I'm going to require that msg.sender is either Alice or Bob. And then I'm going to say no matter who called this function, just pay Alice half of the money and pay Bob the other half. So Alice.transfer address this balance. So whatever balance I have divided by 2. Now this is integer division, so it might not be exactly half, but let's forget about that small detail. And then I say transfer to Bob the rest of the balance. But the balance is already updated, so I just have to say address this balance. Now I'm getting an error because Alice and Bob were not payable. So let me make them payable. Address payable. And this one is also address payable. And then here I have to put payable. Still have some errors because address payable 0. That doesn't work. Okay, I have to do this. Yes, payable address 0. Yeah, the types in Solidity are always a headache. Okay. So now you might think that this is fine, right? No one can do an attack here. Do you see any attacks? Do you think there is a problem with this contract? Well, again, the problem comes in when either Alice or Bob is not an externally owned account, but another contract. So let me just look at this Alice's contract, and let's forget about bribing the miner. Let's say that it can just register in this joint account, okay? So I'm going to first deploy joint account. So I deployed it, I have it at this particular address. And let's say that I also deploy Alice's contract. And Alice's contract is going to sign up in joint account. Oh, okay. So another point is that, well, Alice's contract should also have a way of calling withdraw. Okay, I don't need it right now. So let's say I deploy Alice's contract anyway, and I'm going to copy the address of my joint account, and I'm going to say, with Alice's contract, I'm signing up in the joint account. So if I ask for Alice, Alice is now this contract. And let's say that I switch to Bob here, and Bob also registers in the joint account. So if I ask who's Bob, Bob is now the address ending in CB2, which is this one, okay? So Bob is a real externally owned account. It's a real person, but Alice is now this contract, okay? Now let's say that Bob wants to call withdraw. Or actually, let me first deposit some money. So using Bob, let's say I deposit 5 Ether, okay? And then let's say I want to do the withdraw. And if I do withdraw, I expect that 2.5 Ether is paid to Alice, which is that contract, and 2.5 Ethers are paid to me, right? But I do withdraw, and did you see that in the log? The transaction has been reverted. It actually didn't work. Now, why is it that it's not working? Well, the problem is with this one, Alice.transfer. Whenever you transfer money to a contract, it's actually always a function call. Now, this is a very peculiar thing in Ethereum, and it's the source of a lot of attacks and vulnerabilities. So every contract should have a function called receive. And whenever you send money to that contract, you automatically call the receive function. Now, there is this website called Solidity by Example, and you should definitely go and look into this. So it explains all of these things. It also explains receive, I guess, or maybe it's in fallback. It explains fallback. So basically the way this works is that you should have a function called receive, and it's written just like this. It's external, and it's also payable. And this function is called whenever someone tries to pay this contract. Okay, now why do we have this? Because we generally don't like money to get stuck in contracts. So if we just allow anyone to pay the contract without calling any of the functions of the contract, they might pay it by error, and then the money gets stuck, right? But at least doing something like this, the contract can control what happens when someone pays them money. Okay, so whenever you pay money to a contract, the receive function is going to be called. And in this case, because my contract didn't have a receive function, I could not pay this contract. So when I was transferring money to this contract, that was throwing an exception. And when this function withdraw was trying to do the transfer, it threw an exception, so it reverted withdraw itself. So the entire transaction was reverted. Okay, so with this new version where we have the receive function now, let's do the same thing again. I'm going to first deploy the joint account. Then I'm going to deploy Alice's contract. And then I'm going to say that Alice's contract signs up in the joint account. And let's say This was Bob, right? So Bob also signs up in the joint account. So Alice is now this contract, and Bob is this account. Okay. Again, let's say that Bob deposits 5 Ether into the joint account. So the balance of the joint account is now 5 Ether. And if you look at the balance of Bob, it's almost 90. So let's say now Bob calls withdraw. So when Bob calls withdraw, this time it succeeds. And then the balance of the joint account becomes 0. Half of it is paid to Bob. So Bob has almost 92.5. Again, it's almost because he's also paying for gas. But the other half is paid to Alice. And Alice was this contract. So as you see, the balance of Alice's contract is now also 2.5 Ether. Okay. Great. So we have to make sure that we have a receive function if we want to receive money in our contracts. And generally, so I would not write functions like this anymore. I wouldn't write my own deposit function. I would just use receive. Okay. But now this also opens us to another attack. So let's say that Alice is dishonest and she wants to make sure that Bob cannot withdraw any money. So she can just write her receive function so that it throws an exception, right? Actually, I can just write throw here. It will throw an exception. Or I can just have a requirement that cannot be satisfied. Require 1 is equal to 0. Okay. So if I have something like this, again, let's do the same thing as before. Let's deploy joint account. Let's deploy Alice's contract. And let's tell Alice's contract to sign up in the joint account. And let's say that now this one is Bob. So Bob is going to register in the joint account. Let's say he's going to put 10 Ether into the joint account. And now let's say he wants to withdraw. So I call withdraw. And as you see, the transaction has been reverted to the initial state. So here what happened was that Bob called withdraw. This requirement was satisfied. So the transaction was not reverted at this point. Then the transaction tried to transfer half of the balance to Alice. But transferring to Alice calls the receive function of Alice if Alice is a smart contract. And the receive function of Alice throws an exception. So because this throws an exception, the exception is propagated and the withdraw function also gets reverted. So Bob cannot get any of his money. Now in practice, of course, the way this would be an actual attack is that Alice will have a flag called attack, which is, let's say, true. And here I will have if attack do this. And then maybe I will have another function that can basically disable the attack and can only be called by Alice. So I can have function, let's call it disable attack. This is public. I require that msg.sender is Alice. So let's say this one was Alice. So only this account can call it. And all it does is that it sets attack to false. Okay. So Alice can control whether her receive function in her smart contract performs an attack or not. So now if there is some money in this joint account, Alice can basically go to Bob and she can extort Bob, right? She can tell Bob, hey, your money is locked here. I'm willing to disable the attack and let you withdraw your money if you pay me some, I don't know, some bribe or something. But the really interesting point here is that the situation is symmetric. So Bob can also do the exact same attack. So again, remember when something is reverted, all of its side effects are reverted. So here, if Alice.transfer throws an exception, of course, withdraw will also be reverted. But the same thing happens if Bob's transfer throws an exception. So if Bob was also a smart contract and Bob had a receive function that threw an exception, then when we call withdraw, withdraw is first going to pay Alice. Let's say that goes through, and then it's going to try to pay Bob. But that one fails. It throws an exception, which means that all of withdraw will be reverted, including the transfer to Alice. So Bob can also do exactly the same attack here. Now, in the next session, we're going to see other ways of sending money so that these kinds of attack cannot be done. If you want to see it on Solidity by example, you can actually see it here. So yeah, they have something about sending Ether. You basically have transfer, send, and call. And this is the first topic of our next session.